Hi, this is our final project, robust visual imitation learning under dynamic target shifts via shared autonomy. So first, let's state our problem. In this project, our goal is to reach a dynamic cube. Let's see a demo. So we can see in our task, the cube is moving. So the robot should reach this dynamic cube. Okay. In our course, most tasks focus on reaching a fixed target, but in real-world scenarios, things don't stay fixed. So here, we define three scenarios. The first, fixed cube. Second, cube moves before execution. Third, cube moves during execution. Importantly, we still train everything on fixed cube data, and then test how well the model generalizes to dynamic cases. Let's see how we collect the data. So we can see that when collecting data, the cube is still fixed, and we collect camera RGB data as our input. Now, where is the human component? The moving cube represents human intervention. In real HRI settings, human may move objects, may change goals, or interfere with the robot. So the robot should not just follow a fixed policy. It needs to adapt to changes in real time. Second part, method. We evaluate four different models. It should be here, framework. So the first model is geometry expert. This is also our upper bound baseline. It directly computes distance to the cube and moves straight toward it. The second model is here. The second model is vision behavior cloning. We call it vision BC. This follows what we did in homework 8. So the input is RGB image plus robot position. The model uses MLP-based policy with a vision encoder. The output is action. And our third model is vision plus history behavior cloning. Here we extend vision BC by adding temporal information. Now the input becomes current frame plus two previous frames. The idea is that we expect history may help infer like motion, velocity, or direction. We encode this sequence into a latent representation, then feed it into the same policy network before. The last model, we call it full model, and it is actually shared autonomy via action filtering. This is our key method. Instead of directly executing the predicted action, we first sample candidate actions around the vision BC prediction. Then we evaluate each action using a cost function. Here is the cost function. The C task is reaching the cube. The CBC stay close to our vision BC prediction. The C smooth avoids sudden motion. And here is our implementation of this cost function. Then we pick the best action. So we minimize this cost function. Training setup. So for training, we use 100 demonstrations, and each demo has 400 steps. And what about the model? All models use CNN encoder for images and MLP policy for control. Let's take a look at our model. Okay, okay. And after training, all models converge well. Now, testing setup. We evaluate 4 methods on 3 scenarios, and each result is average on over 50 trials. Okay, the results. We have already seen the expert geometry model performs well, and let's see the other 3. So the Vision BC actually can't perform well when the cube is moving. And history vision history BC. This one is also similar to Vision BC. It fails to catch the moving cube. Okay, let's see our key model, the full shared autonomy model. We can see that it successfully reached the cube. Okay, and let's see our 4 results. So first, in fixed setting, when the cube is fixed, we can see that all models perform perfectly in this task. And when the cube moves, we can see that expert model always give the highest success rate, and Vision BC and History Vision BC is only around 50% success rate. Our full method gives around near perfectly on this task, and this is the results when cube moves during execution. The success rate is similar to the previous one. Okay, key findings. So one surprising result is that we find that history does not help. Even with temporal input, performance does not improve. That's because the environment is fully observable. Each RGB frame already contains full information. So history becomes redundant and may introduce noise. Only when the environment is partially observed, I think the history would help. Connection to our class. This project connects several key topics like imitation learning, behavior cloning, state representation, we use that, vision latent space, and shared autonomy, which is beyond the class. We introduce dynamic target scenarios instead of fixed targets. Okay, last, level of difficulty. Reaching a fixed cube is straightforward and easy for all models. But here we introduce distribution shift, dynamic target motion, and real-time adaptation. This makes the problem significantly harder, especially for models trained only on static data. Okay, that's all. Thank you.